Okay, chapter 10, classroom discussion. We talk about fluids, and for fluids, we mean liquids or gases. Um, and the first question, kind of easy and straightforward. Estimate the volume of your body, uh, considering a certain amount of mass, and you can always connect mass to a volume if you know the density, right? See, there is a hint. You can swim or stay just under the surface of the water, so you have a good idea of your density. You can estimate the density of your body as approximately made of water. It's not, of course, exactly water. There are metals, there are other things that are more dense, but you can think just water. And the default density for water, as we discussed in lecture, is 1,000 kilograms per meters cubed. So consider the density as 1,000 kilograms per meters cubed. And if your mass is about 150 pounds, then it's going to be roughly 75 kilograms. You have to convert to System International, of course, because see, we have kilograms for the density, kilograms per meters cubed, and kilograms must be on top. Kilograms cancel out, and you have meters cubed as a result of your calculations. So 75 divided by 1,000, you have 7.5 times 10 to the negative 2. So that's the actual volume. And I also wanted to give you connection to another parameter, which is not System International, but it is widely used in liquids, and every time you buy a bottle of something kind of fluid, you will probably see the unit of liters, milliliters, or liters themselves. Uh, of course, it's fluid ounces that you would most likely see the first thing in a United States bottle, but in Europe, liters are the uh, units that you will most likely see on the bottle. So see how it's 7.5 10 to negative 2. If it's 75, so move the decimal to the right one time, get the 75 instead of 7.5, and then it's going to be 10 to the negative third, of course, instead of 10 to the negative second. So 1,000th of a meter cubed is considered a liter. So 75 liters. Of course, that's not System International once again. That's the correct answer for volume. For volume, you need meters cubed. So this is your conversion between liters and meters cubed, just in case you ever need it. And of course, Google knows all of those conversions, but just so you know, the one of the alternative measures for volume, for fluids specifically, for those gases, you might see liters, and you have to convert into meters cubed. How high would the level be in an alcohol barometer versus normal atmospheric pressure? Remember I said it was mercury. Mercury is the best choice of a fluid for barometer or manometer because it's going to make everything compact. So why is it so compact compared to, say, alcohol? Well, you need the density of alcohol that you can find in the table, and you have to recall the hydrostatic pressure formula, the rho GH, density of a fluid, and H is the depth. So if you want to measure the atmospheric pressure, the 100,000 pascals, then the height of an alcohol in a manometer is the pressure divided by density and the G. And density of alcohol is slightly less than water. You can see it's about 800 kilograms per meters cubed. That's why alcohol will actually float on top of water, or the water would sink and alcohol would go up if it's not mixed as a cocktail. And G is 9.8. So boom, you get 13 meters, which is like 39 feet. Is that a compact barometer? 39 feet? It's like a height of like a 5-story building. That's definitely not a convenient device to use to measure the pressure by any means. So this is so tall that it's just not practical for many cases. That's why mercury is used instead. Why is it mercury? Because mercury would have a density of 13,500 units. So that would be 13 times greater density. So like it's actually more than 13. So it's going to be like 15, 16 times more denser. And that's why it's going to be 16 times less in size. That's why you'll have a compact device to measure the same kind of pressure, but different fluid, different working fluid. Okay, now the manometer measures the pressure in an oxygen tank. Pressure is 1040 millibar. That's totally not System International. You have to convert to pascals from that. What's the absolute pressure in the tank if the height is 18.5 centimeters higher or 5.6 centimeters lower? So let's draw a diagram and see what's going on. So the first option is the height of the mercury in the open tube is higher. Here's the open tube, and the level is higher, and the manometer is connected to the tank. So the tank is right here. And the tank exerts a pressure on the other side of the manometer, and you see the difference in the level is delta H given. So how do you calculate the pressure? First of all, you say same level for the same fluid gives you the same pressure. So the pressure at this point must be the same as the pressure at that point. And this is the unknown pressure that we want to figure out. And this is the pressure that we can actually measure and calculate, which is the sum of the atmospheric pressure on top of the fluid plus the hydrostatic pressure caused by, mercury at this depth. So this is your atmospheric pressure plus rho GH, density of a fluid is density of the mercury, which you can look up in the table as well. G and the H is given. Be careful, it's in centimeters. You cannot do centimeters. You have to convert to meters. So P sub 0, the atmospheric pressure, you have to convert those millibars. Milli means 10 to the negative third, and bars are connected to pascals as 100,000 units for 1 bar. So bars cancel, you're left with pascals. So you are still at 100,000, give or take a little bit. So still 100,000 pascals after all the conversions. Because if it's 10 to the negative third and you multiply by 1,000, then they kind of cancel each other. You still have like one bar, and 1 bar is 100,000 pascals. So not a big change here. Like I said, every time you see P sub 0, the atmospheric pressure, you can consider 100,000 pascals, and you'll be fine with that approach. So density of a mercury, 13.6 thousand kilograms per meters cubed. That's what the table gives you. G is 9.8. And the depth of mercury is 18.5 centimeters. Remember, centimeters you convert to meters. So 18.5 centi, you divide by 100, decimal moves 2 times to the left. And once you do the calculations, add up all things together, you get the pressure that is slightly greater than atmospheric pressure. That means that this pressure is enough to push the mercury downward, and because of the Pascal's principle, all that extra pressure is transported all the way, and the other side rises to a certain level, so you can measure it and do the calculations. Now, the second option, the second case, is when it's 5.6 centimeters lower. And if it's lower, that means the pressure in the tank is less than atmospheric pressure. Atmospheric pressure wins over it. Atmospheric pressure pushes mercury further down, and the other side level rises, showing you that the pressure inside the tank is less than atmospheric pressure. So not only the change in the level is important, but also which way is the change. Is it up or down? If it's moving up, then atmospheric pressure, loses to the pressure inside the tank. If the level is lower, then atmospheric pressure wins over the pressure inside the unknown gas tank. So pressure in the tank is less if the manometer level is lower, and instead of doing delta H as positive value here, you had 18.5 centimeters on top of the manometer. Now it's going to be 5.6 centimeters below the level. And if it's below, then the change is opposite, the change is negative, and the result is less than atmospheric pressure, which is shown in the solution. You have 96,000 versus 100,000, so clearly less than atmospheric pressure here. So this is your basic idea for measuring the pressure, and the manometer is the tool to do that. Now, this problem is really what it takes. Like, I'm pretty sure when you were a kid, you were wondering, how many balloons do I need to buy so that I can just fly away from mom and dad? Well, now it is time to answer that question. I'll give you the exact number of helium-filled balloons so that a person of about 150 pounds, which you convert into kilograms, can start his or her journey to, I don't know, Disneyland or Legoland or whatever your kid's destination was. So we got a person of a certain mass, a certain amount of helium balloons. Of course, there is some mass to those balloons, and there is a gravity for the person. So two gravitational forces to counterbalance with the buoyant force. Why do we have buoyant force? Because helium has less density than the air. Air is nitrogen and oxygen. Helium is much less in terms of the atomic mass, so less density, and that's why you get the upward buoyant force. Buoyant force is always upward, remember that. So here comes your dynamics, here comes motion. That's the second Newton's law that you're going to use for any kind of motion. Buoyant force is positive because it has the same direction as y-axis. Gravity is negative because it's in the opposite direction to the positive y-axis. And there's nothing about acceleration that is given, just you lift a person, so there's no really like acceleration to consider. So let's just think acceleration as 0, but the overall motion is upward. Now, how do you calculate the buoyant force? What is going on with buoyant force? It's the density of a fluid that the object is submerged into. Be careful, it's not the helium, it's not the rubber that the balloons are made of, And it's not the density of a person, none of that. It's the density of the fluid that the object is immersed into. So this time it's the density of the air. Air is the fluid that the object is, the helium balloons and that little boy is immersed into. Now it's the submerged part of the balloons, not the total, but see how they're completely submerged into the air. So you just say the volume of the helium that you need for the balloons times the G. On the other hand, you have the gravity for the helium, and gravity is mass times the free fall acceleration, and mass is density times the volume. And you can see how this time it's the density of the helium, because we're talking about the mass of the helium. And once again, it's the volume of helium, which turns out to be the same as the right side because they're completely submerged into the air, times the G plus M% G. So G can be factored out and you cancel the G on both sides. So your volume of the helium needed is connected to the density of the air, density of helium, and the mass of a person. That's your analysis of the second Newton's law, the main equation for dynamics. On the other hand, you can calculate the volume of the helium needed for those balloons as volume of one balloon times the number of balloons. You know that one balloon has a certain volume, and it says specifically that a balloon is a sphere with a certain diameter. Be careful, those are centimeters. You can't do centimeters. You have to convert to meters. And the volume of a sphere is 4/3 pi r cubed, in case you didn't know that from the high school geometry. Multiplying by the number of balloons, that's going to give the volume of the helium needed to go into the sky. So from one side, you solve for the number of balloons times the volume of one balloon. That's your left side of the equation. And on the right side, you get the connection between the density of the air, density of helium, and the mass of a person that you can solve for the volume of helium. This is the expression from the second Newton's law. This is the expression from volume of one balloon times the number of balloons. You can set them equal because it's the volume of the helium that we're solving for on both sides. And you solve for the number of balloons doing the basic algebra. There's no more physics here. I'm plugging in the mass of a person, plugging in the radius. Be careful, it's the diameter that is given as 33. You need the radius. Radius would be the diameter cut in half. So 0.165 for the radius. And then you cube it times the 4 pi. And this is the change in densities. So about 3,400 balloons. Well, makes sense because one balloon is definitely not enough. 100 would still not do the trick for 70 kilograms. But eventually you can get, a few thousands of those balloons and you will beat the gravity. It's totally possible to beat the gravity. In fact, I'm pretty sure you've noticed that there are hot air balloons in the sky, some festivals, some gatherings. You have those carnival attractions. You can actually still experience it. It's like not safe at all. Be careful while you are on that hot air balloon. There's a lot of risks, so it's not really the best way to travel. Back in the days, people used them all over the place to see if the enemy is coming or if for weather monitoring. Still, the point is, from one perspective, it's the second Newton's law that everyone remembers because there is dynamics, there is motion and you can do the analysis of forces. And on the other hand, it's a very specific buoyant force, which you can't mix with any other forces, because see how buoyant force, it's all about the fluid itself. And for gravity, it's the object itself. And if it's a helium balloon, it's the helium, not the air outside. But for buoyancy, it is the air outside, not the helium. Be careful with subscripts, be careful with notation. And some geometry from the sphere, spherical looking objects. Okay, we discussed the Bernoulli's principle, and one of the applications was the explanation on the uplift force on the wing on an airplane. I actually have some numbers for you, like real world numbers, to see how this works for a certain aircraft. The wing has a certain area, about 88 meters squared. This is like a large, quite large aircraft, maybe Boeing, I don't know, 777 or Airbus 360, 370, I don't know, like the largest one. And as I said before, greater distance is traveled on top of the wing. Less distance is traveled below the wing. Greater distance with respect to the same time means greater speeds, greater velocities. So the air travels faster on top of the wing, and it travels slower at the bottom. And Bernoulli's principle says what? The more the speed, the less the pressure. That's exactly what you have on top. And the slower the speed, the higher the pressure. This is your conservation of energy for fluid dynamics. So it's lower pressure on top, higher pressure at the bottom. Boom, you have the uplift force, similar to what we have for buoyant force. It's always upward. So speeds are actually given. You have 280 on top and 150 at the bottom. Let's figure out how much of an uplift we're going to get. Remember the definition for pressure, it's force per area. So you do have some pressure on top, which is the force in the area on top versus the force at the bottom. Force at the bottom is going to win because of the higher pressure and less speed, less velocity. So the analysis of two equations tells you to solve for the force as change in pressure times the area, because the area is the same. Force is pressure times the area. Force is pressure times the area. So change in pressure times the area creates this uplift force. The difference in pressure can be found from Bernoulli's equation. And if it's the same surface of the wing, so same height above the ground, approximately same, of course. Above the wing is going to be a little more versus what's below the wing, but the difference is minimal compared to the altitude that the aircraft is traveling at. So you can consider a potential energy being roughly the same. If you'll take care of it, your answer will not really change that much anyways. So considering potential energy being the same on top and the bottom of the wing, you have pressure plus kinetic energy density equals pressure plus kinetic energy density, top and the bottom. You can see how algebra works. You transfer P sub 2 to the other side, you transfer density to the other side, factor out the density here, and you get the, first of all, density of air, it's about 1. Remember, the density of water is 1,000, and density of the air is about 1. It's 1.3 to be more specific, but it's just another thing you might want to keep in mind. No matter what, density of air is 1,000 times less than you have for water. So change in velocities produce change in pressure, and change in pressure turns out to be about 36 kilopascals, which is not that big of a deal compared to atmospheric pressure. But let's not forget that you're going to multiply it by the area of the wing. And if the area of the wing is about 88, then the overall product between the two numbers produces an uplift of 3 million newtons. Very respectful uplift force. We're talking millions of newtons now. Remember Mike Tyson? Mike Tyson hits 10 kilonewtons. This time we're talking meganewtons, which is, thousands times more than the Mike Tyson hits his opponents with a knockout. So this force can counterbalance quite a gravity of massive cargo. You can transport, what is it? If it's mg, so you can, cut the g, so it's 10 to the fifth. You can transport about 300,000 kilograms of useful load. 300,000, okay? 300,000 kilograms of mass with this uplift, which is a lot of passengers with a lot of cargo flying to, I don't know, Hawaii or any other destination that you can think of. So this is your basics for constructing an aircraft for a certain load. You would go through the definition of a pressure, and then the Bernoulli equation allows you to solve for anything. Now you have the pressure, you have the velocity top and the bottom, so the geometry of the wing also plays a part. Depending on how much of a change in velocity you want to produce, you will create a wing that is capable of producing that change. And it's a straightforward math, no calculus here, as you can see. You can, come up with a very reasonable number right away. And this is your first step for manufacturing an aircraft. Oh, and that was the last thing for problem solving here. Textbook has some more samples and you have homework to do. Once again, I really want to keep it as introductory level. So on the test, you will see some just basics. The Archimedes principle is the next lab, and the calculation of pressure at a certain depth, nothing else. So just do your homework, read the book. You should be in a good shape for the next test. Let me stop the recording.